Okay, good morning, folks. I've got 3 minutes past the hour, so we should probably go ahead and get started. I don't think I have anything on my list of logistical items that we need to discuss this morning. You know that homework 6 has been assigned. That is nominally due this Friday evening. If I have a chance today, will write up some notes on contour integration and put those online as a review for you guys to help you out with I believe it's problem 1C, where you're doing a Fourier transform by residues. Is there anything else that you want to discuss logistically before we get into the physics for today? Okay, if not, then let's remind ourselves what we talked about last time. It was overly optimistic to think that we could wrap up time-dependent perturbation theory in one lecture and get a significant part of the way through atoms and external fields. So this is now atoms and external fields part 2, and that will probably push the schedule back by a lecture or so. The line between time-dependent perturbation theory and scattering theory is a little fuzzy, so we'll see what that ends up doing in terms of the next midterm down the line. So last time we finished up talking about time-dependent perturbation theory. We discussed the adiabatic approximation when the time dependence is very slow, and what happens to a quantum state if the perturbation is very slow. What does the quantum state do as a function of time?
It'll stay in the ground state.
If it started off in the ground state, it will stay in the same ground state as a function of time. If it started off in the n=3 state of the harmonic oscillator, it will stay in the n=3 state as a function of time. So if I had the harmonic oscillator and I changed the frequency very, very slowly, it doesn't always have to be the ground state, but it stays in whatever relative state it was in. That's right, and that happens physically because you change the perturbation very slowly, so slow that it doesn't have time to jump to another level. And that's equivalent to saying you change it so slowly that the frequency that you are using to change it is very low and you're not adding very much energy to the system. The other limit we discussed was the sudden perturbation. What happens in that case? If you have a system in a quantum state and I suddenly instantaneously change the potential very violently?
The state won't have time to react, so then it'll need to go to a different energy level to fill in the potential?
That's right. So the system doesn't have time to react, so it stays in exactly the same quantum state it was to begin with. So if you start off with a harmonic oscillator in the n=3 state of some frequency, and then I double the frequency all of a sudden, right after I do that, it's still in the original n=3 state of the original frequency. It did not respond at all. So those are the two cases that we discussed. The adiabatic limit, very slow, where it slowly and continuously relaxes to the new state as a function of time. And the sudden perturbation, where the system does not have time to transition at all. We also discussed an application of time-dependent perturbation theory to a problem you've seen and solved before exactly for homework, which was the case of paramagnetic resonance. That was the case when you had a spin in an external magnetic field that's precessing around it, and then in addition, you add another transverse magnetic field that's rotating along with the spin. And in the exact solution, you found that if the rotating magnetic field rotates exactly in phase at the same speed that the spin is precessing, then you drive it to resonance, which causes it to tilt down away from the z-axis and eventually flip from being spin up to spin down. And we saw essentially the same physics reflected in time-dependent perturbation theory, that at resonance, the rotating magnetic field can drive a transition from being spin up to flip it to spin down. In the last few minutes of class last time, we discussed the Zeeman effect, which is the simplest way that an atom couples to external fields. The Zeeman effect describes the coupling to an external magnetic field. And as such, it describes the coupling to the spin angular momentum and the orbital angular momentum. It almost looks like it's coupling to total angular momentum J, except for the factor of 2. That factor of 2 is the electron G factor. So it's not just addition of angular momentum because you don't weight the contributions equally. And we saw at first order in perturbation theory, what this does to the hydrogenic levels is it splits them based on this combination of the eigenvalues, Lz plus twice Sc. So for S wave states where L is equal to 0, the effect was it split a single state into two states, spin up and spin down. For the 2p state where you have both spin and orbital angular momentum, the splitting was much more complicated. that split the various 2p states into 5 states, corresponding to LZ plus 1 and 2SZ plus 1, as well as minus 1, 0 plus 1, and then anti-aligned plus 1, minus 1, or vice versa. So today we will continue that discussion with the interaction of an atom with an external electric field, and this is known as the Stark effect. So, of course, the way that an electric field couples to a charged system like this is through its multipoles. So if in my classical simplistic picture of the atom, I have a proton and I have an electron that's orbiting around it, the fact that I have positive and negative charge at different points in space means that I have an electric dipole moment. So this electric dipole moment D So this is defined, it's sort of like a center of mass vector. So it's weighted by the charges. I have a charge plus E, and the position of this guy is at the origin. Plus I have a charge minus E, and this electron is at position R. So the proton doesn't contribute anything to the dipole moment in this frame of reference because it's at the origin, and I get the dipole moment is minus the electron charge times the position of the electron. So keep in mind that even though we're usually talking about the position R of the electron, since it's negatively charged, the dipole moment that drives the Stark effect is actually opposite to that. So if the dipole moment is related to the position vector, in quantum mechanics these will be position operators, then the coupling of an external magnetic field to it is minus electric dipole moment dot product with the external electric field. So this is what you get at first order in perturbation theory. If your system has an electric dipole moment that is non-zero, then you simply couple to the existing electric dipole moment. So much like the Zeeman effect, where you have a magnetic moment that wants to align with the magnetic field, here you have an electric dipole moment that wants to align with the external electric field. So this is an alignment energy of a dipole with external electric fields. You can think about this as being the effect of the Stark effect at first order in perturbation theory, where if you have an electric dipole already, then you can align that dipole with the external field. But many atomic states do not have an intrinsic dipole moment. So for something like the 1s state of hydrogen, so in this case, the example is spherically symmetric. If I have a 1s state that looks like this, I have a proton density in the middle, and I have a nice symmetric distribution, which is spherical, then my net dipole moment is 0. And in this case, the effect of the electric field acts at second order. At first order, there is no electric dipole to couple to. But as we'll see, when we turn on the electric field at second order in perturbation theory, first, the electric field can create a dipole moment. So the first effect will be that you will polarize the electron distribution. So you will take this, and in the influence of an external electric field, let's say this way, that electric field wants to push positive charges towards it and negative charges away from it. So this external electric field will actually shift this electron density, something like this. And that will create an electric dipole moment.
And you said this is for the second order?
Sorry, say again?
And you said this is for the second order in perturbation theory?
Yeah, we'll see quantitatively how this works in a minute, but you can say, if I take this operator, this is my Hamiltonian. Let me say this is plus E electric field dot product position vector operator. At second order in perturbation theory, then we'll have two insertions of this. So there will be one E dot R and another E dot R. So this is an E squared electric field squared effect. And I'm trying to argue with you that the effect of that electric field is doing two things. The first order is creating a dipole moment, and the second electric field is interacting with that dipole. So the first effect is you have an electric dipole moment that is induced. D induced is some coefficient, let me call it alpha, times the external electric field. So you create an induced dipole moment because of the electric field. And then the second order energy will be something like, let's say the energy will be something like minus the induced dipole moment. Let me put a squiggle here because I'm not going to get the factors precisely right. Dot product with the electric field. So this is going to overall look like something alpha times electric field squared. One of the electric fields creates the dipole moment. The second one generates the energy of the dipole moment in the electric field. That's why it's a second order effect. Does that make sense?
Yes.
Yes, okay. So let me maybe be a little more precise about this. So suppose I do it differentially. Suppose I start with a system that has intrinsic dipole moment equal to 0. And I turn on the electric field differentially. So in that case, I will create a dipole moment, sorry for the notation, a differential sized amount of dipole moment, D. This is going to be some coefficient, which is referred to as the polarizability, times the amount of external electric field that I turned on. So then I ask, what is the change in the energy from this? The amount of energy that's acquired from turning on this polarization is minus the differential sized amount of electric dipole that I create, dot product with the external electric field. So this is minus alpha E dot D. And if I integrate this, so by the way, this is minus 1/2 alpha differential of E squared. And if I integrate this expression now from E equals 0 to some final value E, then I get a more precise version of what I was writing there on the right side. The overall energy of alignment is minus 1/2 alpha E squared. So it's just like work. If you had a spring, some linear force law, which is more or less what this is, an energy that's proportional to the external electric field, proportional to the force that's applied, then the total amount of work and the total amount of spring potential energy is 1/2 kx squared in the same way. So the spring constant, if you like, about that electric separation is what's referred to as the polarizability. In general, you can expand on this idea for an object that has, complicated rotational structure. The most general version of this that I could write would make this alpha a matrix, referred to as the polarizability tensor. So the energy in an external electric field would be 1/2 alpha ij, electric field I, electric field j. So this would be a funny system where I apply the electric field along x and I generate polarization along y. Simple systems don't do that, but you can imagine a complicated matrix that might. Okay, so this is the physics of interacting with an external electric field. The first order, the most important effect is if there is already a dipole moment, that dipole moment aligns with the field. That is a first order effect because it has one power of the external field E in it. At second order, if there was not already a dipole moment, you create a dipole moment. And you can see why this effect will always lower the energy. You will always create a dipole moment, and that dipole moment will then be more stable because of its interaction with the electric field. So this is an example of how second order perturbation theory will lower the energy of the ground state by turning on the electric field to create a dipole moment and then aligning that dipole moment to stabilize its energy. Okay, so let's talk now quantitatively about how that works in quantum mechanics. Everybody with me so far on the essential physics of atoms in the external electric field?
Yeah.
Okay, great. So the Hamiltonian that we want to consider in this case is a Hamiltonian that at the 0th order, the bare Hamiltonian is the Coulomb potential. And the perturbation that we're considering from the external electric field is plus electron charge electric field dot position operator. So the first order spark shift of an atomic state in perturbation theory. So this would be energy at first order, let's say NLM. The spin doesn't have anything to do with this interaction with the electric field at this order. This is just the expectation value in that quantum state of this perturbation. So that is H1, the perturbation, NLM. So this is plus E electric field dot NLM position operator R NLM. And so everything that we're going to discuss for the next little while is about how to evaluate an operator like this that actually looks really simple, but has a lot of structure to it. This is a topic that will synthesize many things that we've been discussing throughout the semester. The first thing that I want to highlight is that this operator is a vector operator. And we know something about vector operators and angular momentum. This vector is a three-component operator, Rx, Ry, Rz, that corresponds to three levels of angular momentum. How much angular momentum is being carried by this operator that has three components? If this were a spin state and it had three levels, how much angular momentum would it have?
7.
I heard something, but I couldn't tell what it was. What's the value of the spin has three components? It's not spin 0. Spin 0 has one component. It's not spin a half. Spin a half has two spin states. What spin has three spin states?
1.
Spin 1. So we discussed this in lecture 5 about operators that carry angular momentum in exactly the same way that a three-level system carries 1 unit of angular momentum. A three-component operator, which is a vector, carries 1 unit of angular momentum. So the first complication, or the first important feature about matrix elements of this type, is that any vector operator, no matter what it is always delivering 1 unit of angular momentum to the system. So this is analogous to, if I have spin equal to 1, then I can have SZ equals +1, 0, -1. That's 3 states. The number of the independent components is the same as having a vector operator V, and I have components Vz, Vx, and Vy, which it's actually much more convenient to split these up into combinations that look like this angular momentum. Vx plus I Vy, Vz, Vx minus I Vy. Again, this is 3 states. These three combinations, either in this basis or in the other basis, are reflecting the fact that this carries 1 unit of angular momentum. Exactly like adding another spin angular momentum with s equals 1 into your state. So let me remind you these results from lecture 5. For any vector v, we can split that vector operator up into components that carry definite amounts L and Lz of angular momentum. I believe we wrote them at the time something like VLM, where this L is the quantum number telling you the magnitude of angular momentum. And this M component is a quantum number telling you the Z component of angular momentum, exactly as if having an additional quantum state with quantum numbers L and M together with whatever state that you had to begin with. Right, so something like this state V acting on a quantum state psi acts like I have now added in another degree of freedom that carries exactly total angular momentum quantum number L and Z component quantum number M that gets added in together with them exactly like addition of angular momentum. The specific combinations that we found before in this notation, combinations that carry definite magnitude and Z components of angular momentum. So the specific combinations that we discussed before is that the Z component of any vector is exactly the component that carries L equal 1 unit of total angular momentum, M equals 0. So this does not change the Z component of angular momentum, but it can jump you from one ladder to another by L equals 1. And just like I wrote over here, the combinations of X and Y that carry definite +1 and -1 units of angular momentum are the circularly polarized combinations. So that was this one, and if I invert an expression like that, I can write the X component is 1 over root 2 V1 minus 1 minus V1 plus 1. The X is, Vy, I already wrote the X, is I over square root of 2 V1 plus 1 plus V1 minus 1. So X and Y components of vectors carry L equals 1, and they must change the Z component of angular momentum, either up 1 or down 1. So in both of these cases, this is L equals 1 being added by the operator, and M equals plus or minus 1 being added to the operator. So if this discussion, which by the way goes with the term spherical tensors, that's the term associated with taking a vector or a Cartesian tensor like this in terms of X, Y, and Z components and splitting it up into spherical harmonic type components. If this seems a little esoteric, this is physics that you understand very well, addition of angular momentum. Just understand that when you have a vector operator in between, that vector is adding angular momentum to the states. So with that in mind, this constraint that the operator itself is adding angular momentum is going to tell us that many of those matrix elements are going to be 0. Only matrix elements that satisfy conservation of angular momentum can be non-zero. So because the position operator carries 1 unit of angular momentum, if I have a position operator sandwiched between two different states, NLM, N prime, L prime, M prime, I know something about these matrix elements. I start off with angular momentum L and component M. I add to it and depending on which component of the vector I'm talking about, I could add m equals 0 for the z operator, or I could add m equals plus or minus 1 for the x and y components. So because this thing must add 1 unit of angular momentum, imagine if I had something like, I don't know, how about j equals 2, and I put that together with an extra angular momentum L equals 1. If I started off with a ladder that has j equals 2, and I combine it with a ladder j equals 1, L equals 1, then the allowed states that I can get out of this would be something like, let me call it capital J equals 3, capital J equals 2, capital J equals 1. Right? I imagine the three components of this ladder adding on to this one. So if they add in phase, I can go from 2 up to 3. If I add the 0 component, I can stay at 0. If I add minus 1, I can go down to 1. So if this is the angular momentum state that I start off with, and I add another one, then the only values of L prime that will not be 0 are the ones that are allowed by addition of angular momentum. So this combination will be 0 unless L prime equals L plus 1, which is this case, L prime equals L, which is that case, or L prime equals L minus 1, which is that case. This is the origin of selection rules. This particular selection rule is a consequence of addition of angular momentum or conservation of angular momentum. So right now, this statement only uses this part of the equation. If I split up this vector and I talk separately about z versus x and y, I can also use this component of the information. So more generally, the angular momentum sum rules, the angular momentum selection rules, will tell me that if I have any state, n prime, l prime, m prime, and I put the z operator in between it, n, l, m, this will always be 0 unless first I have to have L prime equals L plus 1 or L minus 1. That's the total allowed angular momentum that I can form from ladders. And the z component M prime must be equal to the original one, right? So the z operator adds 0 z components. So M prime must equal M. The corresponding statement is if I have N prime, L prime, M prime, and then X, or Y, it doesn't really matter which one. This guy is going to be equal to 0 unless I have L prime equals L plus 1, L or L minus 1, and M prime must equal M plus or minus 1. So the Z component must leave this M alone. X and Y must change it by plus minus 1. There is no other choice. So we've done lots of work around addition of angular momentum, but this is the first time we've had to really use the operator version of addition of angular momentum. Is the physics of this clear? I want to make sure this analogy between starting with this quantum state, adding in another angular momentum whose value is 1, and what kind of ladders you can get out of it makes sense and connect to these rules for Z and X and Y. Does that make sense or no?
Yes.
Yes. Okay.
And we can
Yes.
move between any two ends. Principle.
So this angular momentum argument doesn't tell you anything about n and n prime.
Yes.
So it could change between ends, it could leave ends alone. That depends on the details of the Hamiltonian. But addition of angular momentum alone, this doesn't even have to be n. This doesn't even have to be hydrogen levels. This can be any rotationally symmetric potential.
Yes.
As long as you write it in a state that starts off with definite angular momentum, you add definite angular momentum, and you select on a state that has definite angular momentum, you have to satisfy the addition equality, right? This angular momentum plus this angular momentum equals that angular momentum, no matter what else is going on with the other quantum numbers. Okay? So this could be the three-dimensional harmonic oscillator, and it would still be the same. Okay, so this is the first complication associated with the Stark effect that makes it much more sophisticated than the Zeeman effect. It couples to the orbital degrees of freedom, and because it couples to that vector operator for the dipole moment, it has specific selection rules associated with addition of angular momentum. We can even do a little bit better than this. We can cut down on some of these possibilities by using another symmetry of this operator, and that is parity. We've talked about parity a little bit informally thus far, so let's make it a little bit more formal. Because the fact that the position operator changes the parity of a state will allow us to further impose restrictions on those selection rules. What is parity? A parity transformation is best defined on a position basis. A parity transformation or a parity operator, I'm going to call that curly P, acting on a position state R. By definition, parity takes this state and changes its position vector by a minus sign. This corresponds to reflection about the origin. Unlike most of the symmetry operations that we've discussed this year, which are continuous symmetries, continuous translation symmetry, continuous rotation symmetry, you can rotate by any angle you want, whether that's epsilon or 10 radians. Parity is discrete. You either do it or you don't. That's mathematically reflected by the fact that this operator is so-called idempotent. If I take the parity operator and I square it on the state R, this means this is the parity operator on the state R. The first time I do it, I change the position, and I get minus R. The second time I do it, I flip it back. So I get the same state R that I started off with, and therefore P squared is 1. So you flip the parity and you flip it back. It only comes in 2 versions. Because of this, this operator is particularly simple. It is simultaneously both unitary and Hermitian. So I have P inverse is equal to P, and this is also equal to P dagger. So this is both unitary and Hermitian. And this implies that the eigenvalues of parity, or any discrete symmetry for that matter, there are 3 discrete symmetries in nature: parity, time reversal, and charge conjugation. This part of the discussion will apply equally well to all of them. Because they have this property, they are both unitary and Hermitian, their eigenvalues are plus or minus 1. Any unitary operator had eigenvalues e to the I theta for any complex phase. And if they're Hermitian, they've got to be real. So taking this to be real selects out only plus or minus 1. So states that have parity plus 1 are parity even. States that have eigenvalue minus 1 are parity odd. For our purposes, we're emphasizing the impact of parity on the operator as opposed to the states. Just like any other transformation, we can talk about the transformation on the state or the corresponding transformation on the operator. A parity transformed operator is one that has P dagger, operator P. Now, of course, P and P dagger are the same. You can call it one or the other, and it doesn't really matter. But this is what I mean when I say that that position vector R is parity odd. How do I see that? Let me take the position vector R and sandwich it between two different position states, R1 and R2. Here, let me actually evaluate the parity transformed operator. That's probably closer to what I want to do. P dagger RP between states R1 and R2. When parity acts on this state, I get the operator times minus R2. When parity acts on the bra, I get minus R1. The position operator returns either one of them. So this is minus, let's say, R2. And these are eigencats of the position operator. This object is, of course, a delta function. R1 minus R2. It sets the positions equal to each other. This is the same whether it's minus R1 and minus R2 or R1 and R2. So I can get to this step and then reverse the procedure. Oops, sorry, this is a number, the eigenvalue. So this is minus R2, R1, R2. This is the same delta function as this one. And once I get here, I can put the operator back inside. This is minus R1, R operator, R2. And so comparing what I started off with and what I ended up with, I conclude that the position operator is parity odd, just like you would expect. So just like parity on a position state returns minus the position state, parity transformation on the operator R returns minus the position vector R. So this is what I mean when I say that it changes the parity of the state. That parity condition means that I cannot stay in the same angular momentum state. I have to change the angular momentum by at least one. So before, when we had the selection rules, we had N prime, L prime, M prime, position operator, NLM. Here, let me say Z components. We had L prime equals L plus 1, L or L minus 1, M prime equals M. And we had M prime, L prime, M prime, X or Y, NLM equals 0 unless L prime equals L plus 1 or L minus 1, M prime equals M plus or minus 1. So this parity condition means that if you are in a state with definite parity, that the expectation value is 0. Right, so if my parity operator on this state, NLM, could be plus or minus 1, NLM, I don't even care which one it is. But if this thing has a definite eigenvalue, then if I take it in the same state, Right? If this has definite eigenvalue, then this is plus or minus 1 NLM. Whichever one it is, this one is also plus or minus 1 NLM. So the plus minus cancels in both cases. I'm going to get 0. So for this reason, you cannot remain in the same angular momentum state that you started off with. That takes for this z component and it rules out this possibility. When I just added angular momentum, I could have stayed with the same total L and the same M because I added the 0 component during addition of angular momentum, but that would violate parity. So in addition to the angular momentum constraints, applying parity considerations means that you have no choice. You must change angular momentum by +1 or -1. And then depending on which component of the vector, you can either stay the same z or you can shift z. But you cannot stay in the same one. And it also rules out this case. So you must change angular momentum by 1 unit. So to summarize, this interaction is plus E, electric field dot product with the position operator. It must change L by plus or minus 1 unit. And depending on the component, it may change LZ by plus minus 1 if the operator is X or Y, or it may change it by 0 if the component is Z. So this feature that coupling to an external electric field requires you to change angular momentum is synonymous with saying this operator is itself an operator that has 1 unit of angular momentum. So I would put this side by side with the statement that the photon has 1 unit of angular momentum. That is because the photon is a vector particle, and that's no accident that it comes from a vector field. That is to say, the photon is a spin 1 particle, also called a vector boson. That is what these selection rules are telling us. And we will now use them to calculate the impact on various hydrogenic states. Any questions so far? This is probably the most esoteric part of the discussion. The important thing is, 1, being able to use the selection rules, and 2, understanding that selection rules come from symmetry. It's not new or different information. It's addition of angular momentum the same way you've always done. Okay, with this in mind, I can immediately calculate the first order Stark effect in the ground state. That first order shift of the 1, 0, 0 state is electron charge, electric field dot 1, 0, 0, position operator 1, 0, 0. And without thinking anything else, I immediately know that this matrix element is
0.
0. Because of these selection rules, I cannot start in an L equals 0 state, add 1 unit of angular momentum to it, and get back in L equals 0 state. Equivalently, I can't do it because I'm changing the parity. I start in a parity even state, I flip its parity, and I cannot get back a parity even state again. So the first order Stark shift is 0. This agrees with our intuition from spherical symmetry of the wave function. Let me share screen for a moment. If you plot the probability density of the ground state of hydrogen, it looks like this. It's obviously spherically symmetric. So part of what this statement is telling us, that this expectation value is 0, is that the ground state has no intrinsic dipole moment. Because the dipole moment is 0, the first order start shift is 0. So, if the first order start shift is 0, let us proceed to the second order start shift. Question?
Do you want to stop sharing?
Yes, I want to stop sharing. Thank you. Thank you.
Thank you.
Okay, for the second order start shift, the calculation is more complicated. So for the purposes of this discussion, let's choose the electric field to be pointing along the z-axis. The second order shift of the ground state is sum over all states, n prime, l prime, m prime, that are not equal to n, l, m that I started off with, which are 1, 0, 0. N prime, L prime, M prime, E, Z operator. NLM is 1, 0, 0. Squared over the energy that I have, which is the ground state energy. Let's say the energy of the 1, 0, 0 state minus the energy that I'm going to, energy of NLM prime. So I get some overall coefficients. I have E squared, writing everything in terms of the ground state energy. Let's call this E naught. I know that this summation is 0 unless, start off in 1, 0, 0, the only states that I can go to coming from Z. I must have L prime equals 1. That's the only thing that I can do if I start from 0 and I add 1 unit of angular momentum. I must have M prime equals 0. So I can sum over all possible n's, but I know exactly what the angular momentum terms must be. So I have sum over all n prime, which starts from the first excited state to infinity. And then I have expectation value, n prime, 1, 0, z operator, 1, 0, 0. Squared, and then I know that the energies down here in the energy denominator go like 1 over n squared. So this is not a trivial calculation to do. There are different ways to approximate it. You can calculate, let's say, the first 2 terms in the series directly and approximate the second order shift that way. Another strategy is to say that this energy denominator gets smaller for larger and larger values of n prime. So you can set upper and lower bounds on it by estimating it from the first couple of terms or from freezing the energy denominator and then summing over all possible states. At the end of the day, the exact answer is (1, 0, 0) at second order is minus 9/4 times the Bohr radius times the electric field squared. I want to connect this back to the idea of the polarizability tensor. We said that the interaction at second order is coming from that polarizability. First, the electric field creates a dipole moment, then it interacts with it. So this is defined to be 1/2 times the polarization, or the polarizability, times the electric field squared. So by reading off this coefficient, I think there was a minus sign involved in here. The energy is always negative. So reading this off, the polarizability of the 1, 0, 0 state is 9/4 times the Bohr radius. Excuse me, 9/2 times the Bohr radius. Oh, no. I got my units wrong. Excuse me. This was Bohr radius cubed. That's better. Yes, 9/2 Bohr radius cubed. So I want to link together these ideas in your head of second order perturbation theory. The polarizability is that coefficient. So this is essentially a perturbative calculation of the polarizability. Okay, any questions before we move on to the excited state?
Just one more time. Can you read what the energy timescale is in the denominator?
Here?
Yes.
Yeah, so this is 1 minus 1 over n prime squared.
Okay, that's what I thought.
1 minus 1 over n prime squared.
Thank you.
Sure. Okay, so we found that the Stark effect on the ground state is 0 to first order, and at second order, it generates the polarizability of the ground state. If we consider now the n equals 2 states, now, of course, I have several n equals 2 states. I have the 2s level, which is the state 2, 0, 0, and I have a family of 2p states. P corresponds to L equals 1, so this is 2, 1, and I've got 3 different values of LZ, plus 1, 2, 1, 0, and 2, 1, minus 1. So overall, I have 4 states that make up n equals 2. So let's calculate the first order Stark effect in n equals 2. So for n equals 2, Lm at first order is 2 Lm E Z operator 2 Lm. And based on what we saw a minute ago for the ground state, it would be really tempting to look at this expression and say, I start at L, I add 1 unit of angular momentum, I can't go back to the same state, and I should get 0. Somebody tell me why this statement is wrong.
You can go from 2s to 2p.
Yes, because there are a whole family of n equals 2 states. This calls for degenerate perturbation theory, not regular perturbation theory. So this idea breaks because at n equals 2, I have a whole family of states that I can cause transitions between at the same level. So no, this does not work. Let me show you visually what the problem is. If I do the same thing, I can plot, for instance, the 2, 0, 0 and the 2, 1, 0 states of hydrogen. So this one has a beautiful spherically symmetric state from L equals 0. 2, 1, 0 has, it's not spherically symmetric, but it's got a nice separation where I have equal density above and equal density below. This object has 0 dipole moment. This object also has 0 dipole moment. But that doesn't mean that anything I could make out of them has 0 dipole moment. So there can be linear combinations of these states that will have a dipole moment. Just to flash the preview, this is what they look like. If I take a specific combination of this wave function and this wave function, I can create something that does have a dipole moment, even though this particular choice does not. So remember, when you're doing perturbation theory in a degenerate subspace, you have picked a particular basis, but there is nothing God-given about this basis. The choice to use 2, 0, 0 and 2, 1, 0 was one of an infinite number of choices we could have made to describe this degenerate subspace. Just because that basis itself doesn't have any dipole moment doesn't mean that the entire vector space has no dipole. Is that clear? I want to put the physical idea of degenerate perturbation theory and why you would get the wrong answer next to those pictures. Okay?
Yes.
Yes, okay. Okay, so for degenerate perturbation theory, we said the only way to do it safely is to look at something that diagonalizes the interaction in that degenerate subspace. Now let's apply our selection rules to this operator. If I have EEZ starting from the state 2LM, and I go to the state 2L prime M prime, any possible transition between any of these four, very few of these are allowed, equals 0 unless I have to change L by 1 unit. So I have to start in either L equals 0 or L equals 1 and go to the opposite one. So I have to have either L equals 0, L prime equals 1, or the other way around. L equals 1, L prime equals 0. And what about M? Sorry, this was M and M prime. The Z component does not change the M value at all. So I must have M prime equals M. So if I think about what this operator does to a combination of those states, the form of that matrix is actually very simple. So if I take EEZ and I act on any one of these n equals 2 states, 2, 0, 0, 2, 1, 1, 2, 1, 0, 2, 1, minus 1. So I have 0 everywhere along the diagonal. The only thing that can be non-zero is a transition between the 2, 0, 0 states and the 2, 1, 0 states, this one and this one. So if I set my matrix up this way, the only thing that can be non-zero is that thing and this thing. So there's actually only one matrix element that I have to calculate. And that's the transition to 2, 1, 0 from 2, 0, 0. Because Z is a Hermitian operator, this object is the same. So I could call this, let's say, delta, and this thing is also delta. Okay, in the interest of time, let's not actually go through the integral that gives us this answer. We can set it up maybe and then jump directly to the answer. So this is E times the electric field over 32 pi Bohr radius cubed, integral from 0 to infinity dr times r squared, integral from 0 to pi d theta sine theta, integral from 0 to 2 pi d phi. And then if I look up what the wave functions are from Shankar, I have r divided by Bohr radius, e to the minus r over 2 Bohr radius, cosine theta. The z operator is r cosine theta. And then I have 2 minus r over the Bohr radius, e to the minus r over twice the Bohr radius. So you can set up the integral. It's doable with elementary methods. You integrate the trig functions, you get a number, you integrate the phi dependence, that's trivial. At the end of the day, you get something which is an R integral of a polynomial times decaying exponential, and you can do that one by parts repeatedly. At the end of the day, what you get is that this number delta is negative 3 e times the Bohr radius. So let me plug this back into the matrix and see what structure that this is telling me. EEZ. I'm going to reorder these states so that I put the two deltas side by side instead of having them split up in columns. So I'm going to put the 210 state up here. 200, 210, 211, 21 minus 1. So overall, I got, let's say, E times E, and then I get 0 minus 3AB minus 3AB, 0, 0, 0. Everything else is 0. So sorry for the change in notation. I reordered this matrix to put the two non-zero elements in a little block up here in the corner instead of having them split apart. So what are the eigenvalues and eigenvectors of this matrix? The eigenvalues I can read off. So this state, for instance, is an eigenstate with eigenvalue 0. This state is also an eigenstate with eigenvalue 0. Let me even write it without the extra factor of EE. This is really telling me about the dipole moment. Z on the state 211 is 0 times the same state back. Z on the state 21 minus 1 is also 0 times the state 21 minus 1 back. These states have 0 dipole moment along the z-axis. The non-trivial part of this matrix is that transition. The states 210 and 200 are not eigenstates, but an appropriate linear combination of them is. So what this matrix is telling me is that Z on the state 200 is minus 3 Bohr radii times the state 210. Likewise, Z times 210 is minus 3 Bohr radii 200. They swap back and forth. So if I take an appropriate linear combination of these terms, then I will make something which is an eigenvector. If I take Z times 200 plus 210 over square root of 2. Each one of these,
Is there a sign difference?
No, there's not a sign difference yet.
Between the eigenvalues?
Yeah, so these eigenvalues are the same. We're going to split it up now into two different eigenvalues. Right, so when I act on this state, each one gives me the same thing back, and I get minus 3 Bohr radii. Minus 3 Bohr radii times the same state, 200 plus 210 over root 2. So this is an eigenstate with a negative dipole moment. On the other hand, if I take the opposite combination, 200 minus 210 over root 2, then when I act on the first term, I get negative 3 Bohr radii 200 plus 3 Bohr radii 210 over root 2. That changed the minus sign relative to what I started off with. Right, I should be getting plus 3 Bohr radii back. 200 minus 210, yes, over root 2. seeing this. Okay, maybe I'm standing too close to this to see it right now, but another way to say the same thing is that, so this object here, this 0 minus 3 Bohr radii minus 3 Bohr radii, is the same thing as minus 3 Bohr radii times 0, 1, 1, 0. This is the Pauli matrix, sigma x. And we know what the eigenvalues and eigenvectors of sigma x are. They are this one plus square root of 2, that one, this one minus that one. And the eigenvalues are plus minus 1. So somehow I'm fumbling this at the moment. But the correct answer is that when I diagonalize this matrix, if I write this as 1 over root 2, 2, 0, 0 plus 2, 1, 0, 1 over root 2, 2, 0, 0 minus 2, 1, 0. And then I write the other two states, 2, 1, 1, 2, 1 minus 1. This combination is diagonal, and I get the overall E in front, minus 3 Bohr radii here, plus 3 Bohr radii here, 0, 0, times the same matrix of states back. So just so that you know that I'm not completely crazy, this is what you get. So this was each state separately. When I form the two combinations of them, 2, 0, 0 plus 2, 1, 0. This was the one that had negative eigenvalues. So the dipole moment should be along negative z. And indeed it is, right? So this object has a large lobe with high probability density to find the electron down here. So the average position of the electron is at negative z, negative 3 Bohr radii. The other combination, 2, 0, 0 plus 2, 1, 0, had average position at plus 3 Bohr radii. So you're more likely to find the electron up here. So this state has the electron density at negative z. Because the electron is negatively charged, that means the dipole moment is pointing along positive z. That's what I'm drawing here. So this state, the 2, 0, 0 plus 2, 1, 0 state, has the electric field aligned with the dipole moment. This is the ground state. This receives a negative energy correction from the Stark effect. This state is the opposite one. The electric field is pointing up, but the dipole moment is pointing down. This is the excited state. It has positive energy. Let me stare at this again for a second and see what I did wrong here. I get the same thing. I get minus this, minus that. I should get a minus. I'm not seeing immediately why this is working out.
You're missing a relative negative sign on the second last equation on the blackboard.
Second to last equation on the blackboard.
Yeah,
here.
over there you're missing a relative negative sign.
So I started off with 2, 0, 0. I got a negative 3 Bohr radius here, minus, and then I got another negative 3 here. So then I want to pull out positive 3.
But 2, 0, 0 goes to 2, 1, 0 with a negative 3b, but you're writing it positive.
Thank you. I knew I was doing something stupid. Yes, thank you, exactly. So I get negative 3, and this one becomes 2, 1, 0. I knew it was something stupid like that. Thank you, Nachi. 2, 0, 0, much better. Now I pull out positive 3 Bohr radii, and it works. 2, 0, 0 minus 2, 1, 0. Thank you. I cannot do basic math. Okay, sanity is restored. Basic math works as advertised. And the final picture that I want to draw is the level split. Let me erase this one. Yes. So the overall effect let's split it up between the 1s state and then the 2s and 2p states that get mixed together under the Stark effect. At first order, the first order shift of the 1s state was 0. E1s, let's say E100 at first order was 0. It had no intrinsic dipole moment. Instead, we had to go to second order. E100 at second order was minus 9/4 Bohr radius cubed electric field squared. So if, for example, someone asks you on the comprehensive exam, how does the shift of the first order, how does the shift of the 1s state of hydrogen depend on the electric field? Is it linear or is it quadratic? The answer is the shift in this level is quadratic in the electric field because it is 0 at first order and only shows up at second order, which is quadratic in the electric field. For the n equals 2 states, we had to change different combinations. The eigenstates were the energy of 200 plus 210. This was the state that had minus E Bohr radii. The state 200 minus 210 at first order had plus 3 E Bohr radii. The states 211 and 21 minus 1 at first order had 0 intrinsic dipole moment. So if someone asks you about the n equals 2 states and how they depend on the electric field, these states have an intrinsic dipole moment. They will depend on the electric field linearly. The states that do not, just like the ground state, will have to go to second order. And we haven't done the calculation for it here. As second order. But whatever it is, they will be proportional to the electric field squared. So if someone asks you on the comprehensive exam, how do these different states depend on the electric field magnitude? These states which have a dipole moment depend linearly, first order perturbation theory. The states that are symmetric and do not will enter quadratically in the electric field, which is second order in perturbation theory.
Will we be doing a second order of the non-zero first order shifts?
Say again?
So does 200 plus 210 and 200 minus 210, do they not have a second order shift?
They do. So these guys will also have something proportional to the electric field squared, but this quadratic dependence is very small compared to the linear dependence here. So the whole assumption behind perturbation theory was that this is a Taylor series. So if they have a linear dependence, that dwarfs the quadratic dependence. And only the ones whose leading behavior is quadratic will show up like that.
Okay.
So to finish it up, let me just draw the same picture that we drew for the levels for the Zeeman effect. So we said the 1s state at first order is not shifted. The 2s and 2p states, there are 4 of them. They split up. One of them goes up. One of them goes down. And 2 of them are not affected. So the one that goes up that has higher energy is the 200 minus 210 state. The one that goes down is the 200 plus 210 state. And the ones that are not affected are 21 plus or minus 1. This picture is, of course, corrected at second order where you turn on these effects. But in that first order picture, which is comparable to the one that we drew for the Zeeman effect, there was no shift of the ground state, and you have a splitting of those particular combinations of 2s and 2p that have net dipole. Okay, that is it for today. We finished the discussion of static electric fields and magnetic fields. So next time we will pick up with oscillating electromagnetic waves, and that will bring us to the photoelectric effect. Any questions? All right, if not, thank you very much. Have a nice weekend, and I will see you on Monday.
Thanks.
Thank you, Professor.
Thank you.
I just had one question.
Yes, sir.
Will we be getting a homework this weekend?
Say again?
Will we be getting a homework this weekend?
Yes, I plan to write another homework and post it on Friday.
And that would be on Stark effect and Zeeman effect, right?
Yeah, I was thinking maybe another problem practicing time-dependent perturbation theory a little bit more since we were only partway through that for the last one. And yeah, something along these lines on the Stark effect and the Zeeman effect.
Okay.
Thank you.
Thank you.